Today, I want to just talk about Galois representations. I want to start with an introduction of what they are, how do you build the Galois representations we're trying to study, and then how these things called entanglements come about. So the goal here is to study the absolute Galois group of Q. This is perhaps the goal of all of number theory, is to understand this very large group. And like group theory does, we study groups through representations, and representation theory is a very productive way of studying groups that are complicated. And many of these representations, in fact, perhaps all interesting representations, if you believe things like the Langlands program, should come from geometry in some sense. So one source of these representations come, for example, from elliptic curves. In general, they come from things like motives. But this is a nice motive to work with, is an elliptic curve, which is given here by some Weierstrass equation. In elliptic curves, I'm going to fix ideas just here and talk about Q, but there is work being done for Galois representations starting from a field, from a number field K. So one could replace Q by K and ask these same questions. So the elliptic curves have these beautiful property that there is an addition. So if you have an elliptic curve and you consider the rational points of an elliptic curve, I can give a group structure to those points such that P plus Q is given by this point here. The addition is just defined so that collinear points P, Q, and R add up to 0. And then the main theorem one learns when you do a first introduction to elliptic curves, if you read Silverman's book, then the goal is to prove the Mordell-Weil theorem. In this case, over Q is just the Mordell theorem. In general, the Mordell-Weil theorem tells you that the rational points is a finitely generated abelian group. So there is a finite torsion subgroup, so a finite subgroup formed by those points of finite order, and then a finite number of points of infinite order that generates sort of like what we call the free part of the finitely generated abelian group. In this talk, we're actually only going to talk about the torsion part, which is going to give us these representations we're after. So the torsion in general, if I go all the way to the algebraic closure of Q, the n torsion, so those points such that n times p is 0, this is actually, we'll see in a moment, this is isomorphic to z modulo n cross z modulo n. So there is n squared of such points. By using the addition laws, you can prove that there are n squared points of order dividing n. So for example, for this elliptic curve here, if I look at the 2 torsion, it turns out that all the 2 torsion points are rational points. But when you go in general to another elliptic curve and some arbitrary n, that's not necessarily true. Not everything is going to be rational. So in this elliptic curve, you have the origin and 0, 0 are rational, and then you have some other points over some algebraic extension. And that's where the Galois groups and the Galois representations are going to come from. It's from Galois acting on these points. So as I said, you have that the n torsion over the algebraic closure is isomorphic to 2 copies of z modulo n. And well, the very first question is, well, but what actually happens, what can happen over Q if I don't go all the way to the algebraic closure? What are the possibilities for the n torsion over Q for an elliptic curve? And that's one of the first theorems sort of in this area. One of the first big results in this area is Mazur's theorem that classifies what torsion subgroups can occur. There's only these 15 possibilities. It can be cyclic. The entire torsion group can be cyclic of order n, 1 through 10 or 12. There is no 11 torsion over Q. Or you can have a bicyclic torsion subgroup z modulo 2 cross z modulo 2m for m 1 through 4. And right away, you might ask, well, so can I find elliptic curves, and can I see these point of order 11 that are over some algebraic extension? And then you can start asking questions what is the smallest extension where I can define some point of order 11 for an elliptic curve over Q, for example. And when you go down that rabbit hole, you immediately end up in this theory of Galois representations and trying to understand what are the possibilities for these Galois representations. And that's actually how I came to this field, was from asking myself that kind of question, like what's the smallest number field by degree where I can see a point of order 11 or a point of order 13. For example, this elliptic curve, this one of the simplest elliptic curves out there, has torsion subgroup equal to z modulo 5. It's generated by this point. This point is a point of order 5, and that's all the torsion that there is for that elliptic curve. But then you can ask, like, okay, so where are the other 5 torsion points? Where are those defined? As I said, the Galois group acts on the end torsion, and that is because if I take a point of end torsion and a Galois element, so an automorphism of Q bar over Q, then sigma of P is also an end torsion point. I wrote here the argument, but essentially what happens is that the Galois automorphism and multiplication by n maps commute because the multiplication by n map is actually defined over the rational. So it's defined by polynomials where all the coefficients are rational, and sigma and multiplication by n commute, and that gives you that sigma p is also a point of order n, and therefore whenever you have an automorphism of Q bar, that gives you an automorphism of the n torsion. So we say that the Galois group acts on the n torsion, and that gives rise to our first Galois representation. The representation is defined by sigma maps to the automorphism of the n torsion that sends P to sigma of P. That is an automorphism, and this whole map is a homomorphism. So this is a representation of this group, and you can actually prove this. There's actually a topology to worry about here because this is an infinite group, and this is a continuous Galois representation. Great. So again, recall that over Q bar, the n torsion is z modulo n cross z modulo n. So the automorphisms of this group is just GL2 of with coefficients in z modulo n. Now that is non-canonical because we have to fix basis, a z modulo n basis of this module. And once you fix that basis, then this automorphism group is isomorphic to GL2. That's okay. We all our representations are going to depend on a choice of basis of En, but it turns out that the outcome is that if I choose a different basis, the representation is going to be the same up to a conjugation. So whenever we talk about the image of a Galois representation, the image is only defined, it's only well defined up to conjugation in GL2. So in any case, we had our representation going into automorphisms of En, and now what we have is a representation going into GL2 z modulo nz, which is nice. It's a very nice concrete group. So now these matrices that the image may be, I would like to see those. What matrices do I get? What subgroups do I get in GL2? And what are the possibilities for these images? We understand the GQ through representations because if this, say, was surjective, then that says that there is some quotient of the absolute Galois group that is isomorphic to GL2. And we're going to construct much bigger groups that is going to give us an idea that there is quotients of GQ that are very large, and there are some matrix groups that are very, very large and highly complicated groups. This is just a visual of what's actually happening. So for example, if I have the mod 5 Galois representation on an elliptic curve, the action, you could also interpret this action as an arithmetic dynamical system and just see what is happening with the points. So for example, this is actually what a point of order 5 looks like. If you have a point of order 5, this is geometrically what happens with these point of order 5. And if there are, I can give you examples where you have Galois representations where there is a point that is sent and a sigma in the Galois group that sends P to 2P. the effect would be that 2p goes to, that p goes to 2p, then 2p would have to go to 4p, 4p goes to 3p, and 3p goes back to p. And that's how the action works on an actual point of order 5. Now, these Galois representations, they also have a very nice property, and is that they are compatible. In what sense? In the sense that if M is a divisor of N, then I can construct the Galois representation on the N torsion. I can construct the Galois representation on the M torsion. And it turns out that you can get from the bigger one to the smaller one simply by reduction. There is a natural map from Z modulo N to Z modulo M by reduction modulo M. And that map actually gives you that this diagram commutes. So if you go here and then you just reduce modulo M, then you get the Galois representation on the M torsion. So it's nice that this larger one keeps track of all the ones that come from divisors of N. And that gives you an idea of like, okay, can we do then towers of Galois representations? So for example, when if you pick L to be a prime, then I can think about the modulo L representation, the representation on the L torsion, the representation on the L to the N torsion, the representation on the L to the N plus 1 torsion. So I get an infinite tower of Galois representations in this form. They are all connected through reductions, modulo powers of L. And we would like to put all these together into one Galois representation that keeps track of all of them. And we do that through inverse limits. So what we do is, if you've seen how to construct the elliptic numbers, the elliptic numbers are constructed as an inverse limit of Z modulo NZ, and we can construct what we call the elliptic Tate module, which is the inverse limit of the L to the N torsion subgroups. So what this is, an inverse limit, is just sequences of points, one for each L to the N torsion, such that there is a coherent sequence in that if I multiply by L Pn plus 1, I get Pn. So they are coherent in that this sort of like reduces to this one and P2 reduces to P1 under multiplication by L. So that is what we call the Tate module. And now since the Galois group acted on the L to the N torsion, that Galois group is actually compatible with this inverse limit. And then the Galois group also acts on the Tate module itself. And moreover, since the automorphisms of L to the N were GL2, then the automorphisms of the Tate module itself is going to be isomorphic to GL2 over the elliptic numbers. Now, there's a big choice being made here. I'm picking a elliptic basis of the Tate module. But once you've picked a basis, a compatible basis for the Tate module, then you get this isomorphism. And then our representations that we had before on the L to the N torsion, they are all directed. They're all encapsulated in this representation, the elliptic Galois representation attached to the elliptic curve that captures all the action of Galois on all L to the N torsion subgroups. And so now the question is, okay, so look at this elliptic representation. The image is some subgroup of GL2 over the elliptics. What subgroups do we get? Similarly, this is just for 1' L, but there are more than one primes. There's more than one prime over the integers, and we would like to put all that information together somehow. So we can do what we call Z hat. The profinite completion of the integers is the inverse limit of all Z modulo NZ under the maps, that the natural maps that I talked about when M divides N. There is a map from Z modulo N to Z modulo M. Under those maps, you can do an inverse limit and construct what we call the profinite completion of the integers. And we can do a similar construction of the inverse limit of all the N torsion of an elliptic curve. And that gives me what we call the Adelic Tate module. Great. And just like En carries an action of Galois, the entire Tate module carries an action of Galois. And just like En was Z modulo n cross Z modulo n, the Tate module is isomorphic to 2 copies of Z hat. And therefore, the automorphisms of the Tate module are isomorphic to GL2 over Z hat. That is a gigantic group, a very complicated group of matrices. But we have now a Galois representation of the Tate module, a Galois representation of the absolute Galois group via the action on the Tate module. So that gives me these Galois representations that are called the Adelic Galois representations attached to elliptic curves. And this one carries all the information we want because it has the information, for example, so there is a theorem that tells you that Z hat is actually the direct product of all the elliptics. And in particular, that means that there are maps, there's projections to any one elliptic component. And this map here is that projection. From Z hat, I can project to one elliptic component that gives me a map down to GL2 over the elliptics. And if you go this way and then down to the elliptics, the representation you get in this way is the elliptic Galois representation attached to an elliptic curve. And if I reduce farther modulo L, I get information about the modulo L representation, which is in fact the representation on the L torsion. By the way, there is even more cool information hidden in here in that there's another natural map is you can take determinants. What happens when you take the determinant? If I take the determinant, say here, what I'm going to go is to ZL cross. And now you can ask, okay, then what is this representation all the way down to CL cross? So if I go all the way here, what you get is actually the elliptic cyclotomic character, which is telling you that one we understand pretty well because it's related to the action of Galois on roots of unity, on L-powered roots of unity. So that is a very interesting nugget that you can use to study what Galois representations are possible. Okay, so now that we have this tower of Galois representations, to understand all the action of Galois, to understand the action of Galois on any sort of torsion points, what we need to understand is the Adelic Galois representation of Galois. And so the very basic question is, what is the image? What are the possibilities for the image of this Adelic Galois representation? Now, this is not a new question. Maser, in what's called Maser's program B, there was no program A. The program B is just it's just a section in this paper. Part A there was some discussion about something else, and then part B is this question, which is exactly what essentially what I've mentioned, which is what groups of GL2Z hat appear as images for elliptic curves. He is mentioning this, of course, over an arbitrary number field K. And what I mentioned before is over Q, but we are interested, in fact, over any number field K. What kind of groups of GL2Z hat can we get as images of Galois representations? Now, we've been looking into this problem ever since, since the 70s, and Serre himself proved a very important result in this area, which is the following. If EQ does not have CM, so remember that, what does it mean if E does not have CM if the endomorphisms of E are just the integers? And if there are extra endomorphisms, then we say it has CM. So if E does not have CM, then what happens is that the image of the Adelic Galois representation is open as an open subgroup, which in particular means its finite index in GL2 of Z hat. As I said, GL2 of Z hat is ginormous, So a finite index subgroup is also a very, very large group. And in fact, in the same paper, he shows that GL2Z hat, that the image in GL2Z hat, the index is always at least 2. So actually, you cannot get elliptic curves such that the image of the Adelic Galois representation is all of GL2Z hat. You at least have index 2. And this fact, the fact that the index is at least 2, that is our first instance of an entanglement. And I'll talk about where that entanglement comes from in a moment. But one corollary of his theorem, this theorem is called the open image theorem of Serre. One consequence of this is that if you restrict to elliptics, if the index is finite in here, then we must have that for any elliptic curve without CM, the elliptic Galois representation is surjective for all but finitely many primes L. So if you give me any elliptic curve Q for all but finitely many L, this Galois representation will be surjective. This group is ginormous, and it gives me lots of quotients of GQ that are isomorphic to copies of GL2 over the elliptics. So that gives me information back about what the Galois group of Q is like. And one question that Serre asked, which is now called the Serre's uniformity question, is if E does not have CM, as I said, for all but finitely many primes, this is surjective. So is there a uniform bound for all the elliptic curves? So he asked, is the image, all of the GL2 over the elliptics, in fact, for all primes L bigger than 37? Are there some images that are some elliptic curves where the image is not surjective for an L bigger than 37? We still don't know the answer to that, but we're closer. We're getting closer. More recently, Zewina actually gave a conjectural list of what indices we can have. So it turns out that these indices occur, and then there is some other finite number of exceptions, which he actually also now has a full list of what are all the possible indices. But we sort of understand what indices may happen. What we do not understand completely is why these indices happen and not others. Also, by the way, is important to remark that now Zewina has an algorithm to compute the Adelic image of a Galois representation. And if you go to a place such as the LMFDB at lmfdb.org, you can actually see, for if you pick an elliptic curve in the database, it will give you what the image is in GL2 of Z hat. Now, well, as I said, Serre showed that the image is of index at least 2. So are there elliptic curves where the index is exactly 2? If so, that's called a Serre curve. That's the one of the largest possible images, a maximal image in GL2 of Z hat. And Alina, Kojukaru, Grant, and Jones proved that, in fact, almost all curves are Serre curves. So essentially, 100% of elliptic curves are Serre curves. So there's a lot of them, but at the time, it was one of these like irreducibility proofs, and there were no examples of such. Even though 100% of them were supposed to be Serre curves, there were not like infinitely many examples that we could look at. And one of my previous graduate students, Harris Daniels, actually showed the first explicit infinite family of Serre curves. I believe Serre himself in his paper did give an example of an elliptic curve that was Serre, but not an infinite family of such elliptic curves. Now, what do we know about images of these Galois representations? The very first incredible step came from Jeremy Rouse and David Zurich-Brown, where they proved that if you have an elliptic curve without CM, then the image of the p-adic, so this is for, let me write here in big letters, this is for L equals to 2. So the image of the p-adic Galois representation there are exactly 1,208 possibilities up to conjugation for that image. And they classified, they give you exactly what images are possible and how to find elliptic curves with those images. And it gives you, in fact, that the index divides 64 or 96. And the images are actually defined modulo 32. What that means is that if you reduced your image modulo 32, then once you know what it is modulo 32, you can do the full inverse image to GL2 over the two adics and get what the actual image is. Now, this was in the past, this was, I think, Rouse and Zurich Brown's paper came in like 2014 or so. And more recently, Jeremy Rouse, Drew Sutherland, and David Zurich Brown, now they have a complete classification of elliptic images conjecturally. We still don't know, but we have a conjecture of all the possibilities that can happen for every prime L. So I'm not going to tell you exactly what those images are, but now we know this is the original Rouse and Zurich Brown result. And now we know that, for example, for L equals 3, very recently the classification has been completed. So this does not depend on any conjecture. There are 47 possibilities for 3-adic images without CM. And for the other primes, for 5, for example, there should be 25, but there is one extra image that we think doesn't happen, but it might happen. For 7, actually, very recently, it used to be 3 possibilities that are left to check, but now it's down to 2 additional. So we know there are 17 and perhaps 2 more, and so on. Also recently, 17, for example, was knocked out a +1 that was here, and that's it. Oh, and by the way, of course, there is actually a very big +1 here, which is part of like why Serre's uniformity conjecture is not known, because there might be an additional image, what we call the normalizer of non-split Cartan, that might happen for other primes beyond 37. Okay, so this is the status of all the elliptic images. And as I said, Zewina also has an algorithm to compute Adelic images for any elliptic curve over Q. And in fact, there's a second paper on how to compute these images for elliptic curves over number fields. Now, as you can see, this result is about elliptic curves without CM. And myself, I proved a classification of Galois representations, elliptic Galois representations for elliptic curves with complex multiplication. So when there is extra endomorphisms. And as a consequence of that classification, for example, by the way, the classification is not just for elliptic curves over Q, but for any elliptic curve over its minimal field of definition, an elliptic curve with CM over its minimal field of definition. So you can replace that by E over Q adjoined a J invariant that has CM. So the classification of the representations, it also works for elliptic curves over some number fields. And it says things, for example, over Q, it tells you that over for L equals to 2, there is exactly 28 images that are possible. For 3, there is 17. For these primes, there is 6, and so on. More recently, in joint work with Enrique González Jiménez, and one of my students that graduated last year, Benjamin York, what we've done is actually give an exact classification of each one of these images. So for example, for 28 there is the 2 Adelic Galois images. We describe exactly what the images are, and we describe exactly what elliptic curves achieve those representations. And not only over Q, but you can see that we've also done it for elliptic curves over quadratic fields. We've also classified all the possibilities for the 2 Adelic images. And again, it tells you exactly how to construct elliptic curves with those images. And not only for Q, but for any L that where there is some exciting elliptic image. Now, as I said, there are what we call Serre curves, but there's elliptic curves where you have that the elliptic image, well, let me backtrack. What we saw is Serre's result about Adelic images implied that the elliptic image is equal to GL2 over the elliptics for all but finitely many primes, but there is in fact elliptic curves where it is always GL2 over the elliptics. And in that case, how is it possible to have an elliptic curve where all the elliptic images are GL2, but somehow the Adelic image is not all of GL2 z hat, because Serre proved that the index is at least 2. So what is happening in that case? This is one such example. Y squared plus y equals x cubed minus x is an elliptic curve where every single elliptic image is isomorphic to GL2, is all of GL2. So what is happening in that elliptic curve to give me an Adelic image that has index 2? For that, let me define what is a division field. So for any n bigger or equal to 2, we can define what we call the nth division field. That is the field of definition of the n torsion of an elliptic curve. So you take every point of n torsion and adjoin. I'm missing something here, which is you want Q adjoined all of this. So adjoin to Q the coordinates of every point of order n, and then what you get is an extension of Q that is given by those points of order n. And by the way, by the properties of Galois representations, the image of the n, the mod n representation, is actually isomorphic to the Galois group of these extension of Q. Now, this extension of Q is an extension of Q generated by the coordinates of n torsion points. That is actually completely analogous to a cyclotomic field. The roots of unity are elements such that they're the n torsion in where are they? These are the n torsion in C cross. So if you take the torsion on, in fact, the n torsion in the complex numbers, those are the roots of unity. So this is, in fact, very much analogous to a division field. And remember that the Galois group of a cyclotomic field is something we, every algebraic number theory class starts by doing a lot of work about cyclotomic extensions, and we know the Galois group. The Galois group is Z modulo NZ cross. So we are really interested to know what is this Galois group. And that Galois group, well, it's precisely isomorphic to whatever the image is of the mod n representation. So that's one reason to study these Galois representations. Now, where was I going with this? I was trying to explain where these, well, first of all, where Serre's result comes from. Why is the index, the Adelic index, always bigger or equal to 2? So there's two possibilities. Either the discriminant of your elliptic curve is a square. In that case, it turns out that the Galois group of the 2 torsion can be trivial if all the 2 torsion is defined over Q, or it can be I can't see my own screen with the camera little thingy. Okay, so we can either have that the Galois group of the 2 torsion is trivial, or it can be Z modulo 3. That's in the case when the discriminant is a square. In that case, already the p-adic image has index that is even in GL2, because this Galois group in general is supposed to be S3 if it was as large as possible. So if the image is this or that, this index will be divisible by 2. Otherwise, if the discriminant is not a square, then what happens? Then it turns out that the 2 torsion always has a subfield that is Q adjoint the square root of the discriminant, which is not a square, so this is a non-trivial extension. But by the Kronecker-Weber theorem, this is a quadratic, therefore Abelian extension, so it has to be contained in a cyclotomic field. And then this cyclotomic field, by what we call the Weber pairing, which is actually related to the fact that the determinant of the n the mod n Galois representation is a cyclotomic character. But in any case, the n division field turns out it contains the nth cyclotomic field, which contains this quadratic field. And now this quadratic field is in two places. It's in the 2 torsion and it's in the n torsion as well. And this connection, this intersection of the two, makes it that the Galois group of, say, let's say n is odd here, then the Galois group of the 2n division field is not going to be the direct product of the Galois group of the 2 division field cross the Galois group of the n division field. It's going to be some subgroup of that because they have to agree on some intersection field. So that's how the Galois group of a composite number can be smaller, even if the Galois groups of sort of prime powers or relatively prime numbers are as large as possible, because there can be intersections, there can be entanglements. So we say that the 2 division field and the n division field are entangled. For example, let me give you an example of this literally happening. For this elliptic curve, the discriminant is minus 43, which is not a square. The discriminant, the square root of the discriminant is in the 2 division field. This is also in the 43rd cyclotomic field, and therefore the 43rd division field and the 2nd division field are entangled. So the Galois representation, the p-adic Galois representation and the 43rd Galois representation are entangled by this one field over there. So what that tells me is that in this case, it turns out that the p-adic Galois representation is surjective, the 43rd Galois representation, the 43-adic Galois representation is surjective, but the Adelic one cannot be surjective because modulo 86, the image is not surjective, it's a subgroup of index 2 to account for this entanglement, for the fact that this field is in both places. And in this case, we do have that this is a Serre curve, so the index is in fact equal to 2. Okay, so now let me give you another example. So here is an elliptic curve that has, I noticed, by the way, that I just changed this plus. This plus here is just going to change to a minus, and the arithmetic actually changes quite a bit. The discriminant in this elliptic curve is minus 11. Again, minus 11 appears in the 2 division field and the 11 division field, and then they are entangled. So in this case, it is also true that the p-adic image is surjective, the 11-adic image is surjective, but they are entangled, and the 22, the mod 22 image is not surjective. This one, though, has more properties. This one elliptic curve has that the torsion is actually isomorphic to Z modulo 5. It's, I think, the example I gave you a while back about a torsion subgroup. And so what does that tell me? That tells me that the mod 5 Galois representation cannot be surjective, because Galois, this says that there is a point of order 5 that is defined over Q, and the Galois group will act trivially on that point. It has to fix it because that point is already defined over Q. So that tells me that as a representation, if I put this point as the first point in a basis of E5, so let's say E5 is defined by P and Q, and this is actually, P is a point over Q itself of order 5, then Galois will fix P, and over in matrices with that basis in mind, I will have a 1 and a 0 here always for every Galois automorphism. So this is a far cry from GL2 F5, from GL2 Z modulo 5. It is not surjective, and in fact, it is of index 24 in here. So that tells me that, first of all, the p-adic and the 11-adic are entangled, and that gives me that the Adelic image has at least index 2. But this fact tells me that the index has to be at least 24 times 2. It has to be at least 48. So now we found an entanglement that is accounting for a larger index. But there is more. For this particular elliptic curve, not only I have a z modulo 5 torsion, this elliptic curve has what we say a Q isogeny of degree 25. There is an elliptic curve to another map, another elliptic curve that is a map of degree 25. It is going to this other elliptic curve. And that tells me that modulo 25, the image is still smaller. It's even smaller than I would have predicted by just knowing that there is a point of order 5. And that gives me that this image is going to be at least of index 120 in here, which together with the index 2 that came from 2 and 11 tells me that the index of this image is at least 240. So this is an elliptic curve that gives you some large index that can be explained by the arithmetic properties of the elliptic curve. By the way, there are more, there are indices that are even larger. For example, for this elliptic curve, the index is 2,736. Now, you can try to understand like how bad can these entanglements be? And this is some work that we did, Harris, Daniels, and I did, for example, a while back, was trying to understand how bad can they be? Well, what if I have two division fields that are completely the same? They're just not just an intersection. This keeps pinging. There you go. Okay. So we've seen examples where the division fields coincided in a quadratic extension, but what if they are so bad, the intersection is so bad that they are actually the same field? So for example, this elliptic curve has that the 2 division field and the 3 division field are exactly the same. And it's exactly the same as the 6 division field. It's this field. For this elliptic curve, it turns out that the 2 division field is equal to the 4 division field, and it is this field. So this happens sometimes. So Harris and I decided to try to understand when do these happen. And they happen in the following cases. They happen when, for example, when are there vertical entanglements? So if the p to the n division field is equal to the p to the n plus 1 division field, these happens only actually when p is 2 and n equals 1. Also, trying to study this, we understood also that, well, because of the Weil pairing, as I said, this field contains the p to the nth roots of unity, but when does it actually contain more roots of unity that you expected? And then we came up that the answer is actually that p has to be equal to 2. But that gave us examples which have been actually generalized by Nathan Jones, elliptic curves where you have that the 2 to the n division field actually has more roots of unity that you would expect for every n bigger than 1. These results have also been generalized now by Daniels and Jeremy Rouse, and in a different direction of like what these entanglements can happen. We also looked at horizontal entanglements. So when can p power division field be a q power division field? And it turns out that that can only happen when p is between the 2 and the 3rd division field, as we saw one example of. And if these and these are equal and abelian, then it turns out that either the 2 division field is equal to the 4 division field, or it's because the 2 division field is contained in the 3rd division field. Okay. We actually continued this sort of like search for trying to understand where entanglements come from. Just for the sake of time, I'm not going to cover much of this, but with Harris, Daniels, and Jackson Morrow, we try to understand at least abelian entanglements. So an abelian entanglement, what we mean by that is that if you take an A division field and a B division field, we know that the eighth roots of unity are going to be here, the bth roots of unity are going to be here, and if you look at the intersection of the two, this D, which is the GCD of A and B, this division field is there too, and therefore the D roots of unity will also be in here, but there could be more. What if there is a larger abelian extension in here, something more abelian, that also appears in another division field, then that is an entanglement that is what we call abelian. So we're interested in knowing whether these entanglements happen. And we have a paper where it classifies at least for P and Q. When this is a P division field and this is a Q division field, we came up with a classification that explains where these entanglements come from. They can be coming from the discriminant, like in the Serre case, from complex multiplication of what we call Weil entanglements that we can also classify, plus some sort of other sporadic, let's say, or some other entanglements that are coming from some parametric families of elliptic curves. Now, we can also just remember that the image of the elliptic curve of the Galois representation is isomorphic to the Galois group. And in that case, we have that the Galois group will always be a subgroup of GL2 Z modulo n. Then to explain a large index, what happens is that the Galois group of your n division field will be small inside GL2. So we would be interested to know also, when does that happen? When do you have elliptic curves that the Galois group is small for some reason inside GL2? And one such example, one such reason why this could happen is, well, what if the image is abelian itself or dihedral? That's also something that I think Harry Daniels, for example, has been looking at. What happens if the image of the n division field is abelian? GL2 of Z modulo n is definitely not abelian for larger n, even for n equals 2. But you can, so being abelian will definitely give you a much smaller image. And this is something that Enrique González Jiménez and I captured or studied, that if you have an elliptic curve over Q and an integer n, then the n division field can be, is abelian only when n is 2, 3, 4, 5, 6, or 8. Now, it could be abelian and the smallest possible abelian group, abelian extension, it could be as the nth cyclotomic field. And in that case, n is 2, 3, 4, or 5. And we classified what Galois groups you can get in those cases, a classification, and also, in fact, a parameterization of each case, what elliptic curves satisfy these smaller images. And I wanted to mention this because this result came about because we understood Galois representation. And in particular, the key ingredient here is one, that we understand what are the possible isogenies of elliptic curves over Q. And second, that we understood this came out as a corollary of the Rouse and Zurich-Brown paper, where they classify all p-adic images. The more difficult part was understanding things like the n equals 4 and the n equals 8 cases. But once you understand all the p-adic Galois representations, then you can go through the classification and see which ones of these p-adic Galois representations have an abelian image and for what values of n. For example, you can show that for 16 is not here because there's no p-adic Galois representation such that when you reduce it modulo 16, you get an abelian group as a result. Finally, I'll say that we, with another one of my students, so this is for all elliptic curves, but as I said in my classification of Galois representation, so with complex multiplication, that's for elliptic curves over number fields. So with another one of my students, with Asimina Hamakiotis, who graduated last year, what we did is also classify when is the Galois group of the n division field for an elliptic curve over a number field and defined, and with CM, with complex multiplication, when can the Galois group be abelian? And it turns out that the answer is not very exciting. It just can only happen when n is 2, 3, or 4. And we did give a classification on when that happens. For n equals 3 and n equals 4, it actually happens for elliptic curves that are already over Q. So it doesn't happen over a number of fields. But for n equals 2, for the 2-division field being abelian, you can have some exciting examples. So there is examples of elliptic curves over number fields where you have these 2-division fields being abelian. And I think I'll stop there, and then I'll just take questions.